Okay, AP Physics. This video should help you finish off your packet. One of the last things you have to do in your packet that should be totally new to you is position versus time graphs. You also have significant figures and conversions in there. I hope you've done that in previous courses. I'm not going to spend time talking about that. So you can read that in chapter 1 if you need to review that, or ask me questions when I get back. So position versus time graphs are graphs that show a motion diagram with all of the spots in between every dot. So if you think about this motion right here, this motion diagram's 1 frame per minute, student walking to school. You'll see that they're going a constant speed here. Then they slow down and they go constant speed. Then they speed up a lot faster. And we only show points in time at every minute where that student is at. But the student actually traveled all this distance. And if we started a stopwatch and put more points on here, if we just doubled the number of points or tripled it, eventually we'll get enough points that if we take those distances and transfer them to a graph, we can get a smooth graph that shows where that student is at all instants of time. And that's what a position versus time graph is. It shows where someone is all the time. And I want you to understand where this graph comes from as it relates to a motion diagram. You should know how these two relate to each other. Okay, it's not intuitive. For some of you, it will be, and you'll say, "This makes total sense to me. I don't know why you're even spending time talking about this." And for others, you'll say, "How come this student is going up in the air? I thought they were walking towards school or something like that." You have to pay attention to your axes systems here. Okay, this is the time, and this is where the student's located on a horizontal axis. So at 0, 0, I'm starting right here. 0 minutes and 0 for my displacement. But if we go across here, let's go to 200 here. We're about at 200 when we're at 1, 2, 3, 4 minutes. And so here's our 4 minutes. If I go up right here, this is approximately 200 meters away from our origin. And our origin would be, in this case, if we go back to our little diagram here, students walking to school, maybe they're walking to school from home, and we called the origin home. So at 4 minutes, the student is 200 meters from home. And then if we keep going, maybe we're at, I don't know what we're at here, 1, 2, 3, 4, 5, 6, 7, 8 minutes. I go out to 8 minutes. We should be somewhere close to, I don't know, 450 meters. Looks like that's where we're at. And that's what these are. These are the dots of that motion diagram at the correct spot. And then it's filling in all the gaps so we know where we're at all the time. Okay. One thing I want you to think about for a position versus time graph is that everything has to be connected. There's no gaps on a position versus time graph. Why not? You can't just be traveling along and be 200 meters away from home, and then all of a sudden you're warped to a different spot in the space-time continuum, and now you're 400 meters from home and you continue that travel at a different spot. Everything's always going to be connected. That's the first thing I want you to remember for a position versus time graph. The second thing is you can't be in two places at once. So position versus time graphs have to be functions. And if you remember from your math class, a function is it has to pass the vertical line test. So if I draw a line on this, I can only cross it at one point. At any time, I can only be in one location. If it doesn't pass the vertical line test, then it's not a motion diagram. At least it's not a motion diagram of a single object. You might have motion diagrams that have more than one object on the same diagram, and that's okay. They can overlap each other, but for that single object, you must only have one location at one time. Okay. The other thing I want you to think about is this line. We're doing linear ones here. You'll have lots of linear ones to start out. And eventually we'll get curved ones, and we'll talk more about that with calculus. But right now, just think about what does the slope of this line represent? If you just do the math here, you should know what slope is. Okay, let's just say that this is 200 and this is 3 minutes. Okay, if we want to calculate the slope of this first line right here, it's rise over run. My rise is my distance. So this is my change in my displacement. We're going to call it delta x. And my run here, this is my change in my time, which means that my slope, I'm going to call that m, like you do in your math class. M is equal to my change in x over my change in time. Well, if you remember earlier, we defined that. That's your average velocity. This is just v, our velocity at any point in time. And so in this case, if we did our values here, we get 200 meters. That's how far I go in my rise. And my run was 3 minutes. And this would give us whatever 200 divided by 3 is. that'd be how many meters we have per minute that person's traveling. Okay. I don't know what that comes out to, 66 or something like that, 66.7. Okay. Then if we do that again for this next line, we have a more shallow line and we're going to have a slower speed. In this one, we have a steeper line, we're going to have a faster speed. If you go back to your motion diagram, that makes sense. This is our slowest time, and that slowest time corresponds to right here. And our fastest time, I'll switch colors, is right here, and that's where we have the steepest slope. And then our middle time is right here, and that's our slope that we just calculated. So the slope of a position versus time graph is your velocity. It's how fast you're traveling. Okay, let's look at a couple more here. This position versus time graph represents the motion of a car on a straight road. Describe the motion of the car. You're going to have to do this in your packet when you describe motion. If you just say the car is moving left or right, that's not enough. You want to be specific by reading values from your graph. And so I'm going to start right here, and I'm going to say where my car is located first. My car is located 10 kilometers from the origin. And so if I put this on a motion diagram, let's go back to motion diagrams. If I call this 0, and I'm 10 kilometers from the origin in the positive direction, that's going to be to the right, my car is going to start right here, 10 kilometers away from the origin. And now what direction am I headed? I'm headed back towards the origin. So that means I'm headed to the left. So my next dot on my diagram might be here, and then here. And we're going to constant speed because we have a straight line here. And that straight line, the slope of that line is the same for all of this first stretch, maybe the first 25 minutes or so of travel. The car is going the same speed. So these would be equally spaced dots. We cross 0 right here, and we keep going. And we're going to go how far? We go all the way out to negative 20. So I'm at 10 kilometers here, and now I'm going to go all the way out to negative 20 kilometers. And you would have to describe this in words in your packet. You're going to say a car starts 10 kilometers from the origin, travels towards the origin at a constant speed for 25 minutes, passes the origin for 25 minutes, continues that speed to the left until it gets to negative 20 kilometers away. Then what happens? What happens right here? This is what we want to know when you're describing the motion of the car, all these changes. At approximately 25 minutes, the car has gotten all the way to here, and the car stops. It's just a flat line here. What does that mean? We're not moving with the car. And that's, for some of you, it's going to be hard to see out in a position versus time graph because the graph continues here. Time is going on, but the position is staying the same at negative 20. So for these next 10 minutes or so, looks like maybe 10 minutes, the car just stays at negative 20 kilometers. And then what happens? Then the car starts traveling back towards the origin, and it stops at the origin. This is not a distance of 80. This is a time at 80 minutes we've gotten back to the origin. So the car would turn around, and you could look at your angles here. It looks to me like our traveling back towards the origin might be less steep of a line, and that means I might have my dots a little bit closer together on my way back towards the origin because we're traveling a little bit slower, and we stop at the origin. Okay, that's our motion of the car. Hope that helps there. Okay, one more. See if you can describe the motion for this one. Okay, I always like to go to my axes. We're in seconds, so we're moving relatively quickly here. And we are in the y direction. That's vertical, and we're in meters. So we start out at 50, and we haven't moved at all here for the first, I don't know, maybe 2 seconds. So you could think of someone standing maybe on a mountainside at 50 meters high, or on top of a ladder. That'd be a really tall ladder. Maybe they're in an elevator. That would be a better description here. They're sitting in an elevator. The door has just closed, but the elevator hasn't started moving yet, and now the elevator started moving. And that elevator is moving at a constant speed, and it drops maybe 1, 2, 3 floors, maybe more. 10 meters, that's going to be a lot more than 4 floors. Okay, so we're dropping 30 meters here. That's going to be like 90 feet. So maybe it drops 9 floors here, and then someone else needs to get on the elevator, so it stops, the doors open, and then it just stays in the same spot for the next 10 seconds. The doors close, and it goes back down all the way down to ground level, and then the doors open and everyone gets out. That might be a description of this vertical motion. Okay, make sure you look at your axes and see what the labels are before you start trying to describe your motion. One more here. See if you can describe the motion here. Okay, again, my axes, it's in seconds, and my x is in meters per second. I'm starting out at my origin. I'm going to the right away from the origin at a constant velocity for the first 10 seconds, and then I speed up, going even faster for the next 10 seconds, and then I stop at 40 meters away from the origin, and I'm not moving for the last 10 seconds. Okay. What could that be? You could give a storyline with that. A person running, they start out a sprint for the first 10 seconds, they get warm. Once they get warm, they're going full sprint, and then they stop and rest at the end of the race, something like that. Okay. I hope that helps for your little packet, for your motion diagrams in the packet. I think that's all I've got. Yep. Again, email me questions if you guys have any. I'd be glad to help out.